Hello, everybody. My name is James Cornelison, and I am a postdoctoral fellow at Argonne National Lab, here to talk to you guys about polarization calibration with BICEP3 and ultimately its impact on parity violation constraints in the CMB. So BICEP itself is a relatively small collaboration. We operate two telescopes at the South Pole, whose main focus is on constraining cosmic inflation. But while we're a small group, we're from a bunch of different places, and in particular, the group that is responsible for polarization calibration is myself. Like I said, I'm a postdoctoral fellow at Argonne National Lab. There's Clara Verges, who is at Lawrence Berkeley National Lab, Annie Polish, who is a grad student at Harvard, and we are advised by John Kovac, who is a professor at Harvard. And I also wanted to acknowledge some other folks, particularly Calvin Tsai and Carson Look, who were winter rovers that assisted us in the measurement of the data sets that I'm going to be talking to you guys about today. And then there is Mike Ector and Matthew Petroff, who are assisting us on the measurements for the calibration that are coming up in actually these couple of months for our next measurement set. So, what I particularly wanted to talk about today was a motivation. So, how parity violation affects the CMB and how we can back that out. Then, in the calibrations that are required in order to break the degeneracy between parity violating signals in the CMB and instrumental systematics. And then I'll talk about how errors in our instrumentation can impact our parity violation results, and then I'll go into where the uncertainties come from in the CMB, and then I'll talk about the constraints that we can do forecasts on given all of the above. I also did want to mention that we've got a paper out now. So if you are interested in this, please take a look at the paper. It's still under review. So if you have any questions or concerns, please forward them to us and we will be happy to implement that feedback. Okie dokie. So, how is the CMB affected by parity violation? Well, this results in something called cosmic birefringence, where you've got linear polarization rotating as it propagates through spacetime. So, if you imagine that you're a linearly polarized photon coming from the CMB, as you pass all the way across the universe and hit our telescopes, then if you're of some vertical polarization, that might be non-vertical as it hits the telescope. But if you'll notice that this is actually perfectly degenerate with the telescope, us not actually knowing what the orientation of our telescope is, right? And the way that we actually characterize our telescopes is by installing these large flat aluminum mirrors that redirect the field of view onto the horizon. And then we'll install these calibrators on top of these towers so that we can observe the calibrators, which are, have been designed and are to, exact specifications and are really well understood, so that we can back out characterization metrics or performance metrics on our telescopes. And so the calibration source that we use in particular is called a rotating polarized source, which is a broad spectrum noise source that operates at 95 gigahertz, and it is instantaneously broadcasting across the 10 gigahertz band. And that source, which is located at A right here, is plugged into a rotation stage. And that rotation stage can rotate a full 360-degree axis. And the source itself is linearly polarized, but we use a wire grid to clean up that polarization so that it's a very well-known polarization, right? And then we have a tilt meter that registers the entire apparatus with respect to gravity, and that's what actually allows us to transfer our knowledge of the orientation of the source itself and polarization into an orientation that we can reference in our telescopes, right? And this here is just another image of the source itself actually rotating, so you can get an idea of what that rotation actually looks like. But the way that we actually figure out what the orientation of those wires is by using a reference surface that is both known to both the tiltmeter and the wires, right? So if you know the orientation of the wires, then you know the orientation of the polarized light coming out of your wire grid. And then we use the tilt meter to against that same reference surface in order to back out the polarization orientation with respect to gravity, right? And so actually how we go about making this observation, like I said, we install these calibration sources on top of a tower and observe it by making these rasters across the sky with our telescope. So this is actual telescope data where we've rastered in azimuth and taken steps in elevation to produce this nice curve. And then what we'll do is we'll take that measurement at a given orientation of the source, and then we'll rotate the source across 13 different angles, and that gives us um, 13 different orientations of beam maps is what we call them. And then what we could do is we could fit a modulation curve uh, to these beam maps and back out the phase of this modulation curve actually gives us the angle of our the angle of our detectors with respect to the angle of the calibrated source. All right, so when we actually start to look at our calibration results, I did want to point out that we have about 2,000 detector pairs across our entire focal plane, and those are actually split up into specific tiles, modular tiles that you can sort of swap in and out. So the way that we typically look at them is in this sort of tile format. So when we go to actually look at the angles themselves, you can see they're split across these tiles, right? Um, and so the overall angle that we have on this across our entire focal plane is about minus 2.5 degrees. That 2.5 degrees is pretty arbitrary because that involves some reference point for the orientation of our telescope itself, and it includes the pointing model. So that I think could be largely disregarded. But another thing to look at that is pretty important is the angle scatter from tile to tile, right? So a lot of times we assume that all of the tiles are oriented, in some fiducial sort of orientation with no scatter, and we're actually measuring a scatter on the order of half a degree here, which is pretty significant. In addition to that, we have a pretty high enough precision in our measurement that we can see that there's scatter also between the detector pairs, and that it also includes seeing that there's features within the tiles due to some either fabrication or physical design that something is going on optically in the system, which is really great. Now, for systematic uncertainty, we had considered many different sources of different ways that systematics can enter into our error budget. And we are happy to say that most systematics are actually well understood and within nominal limits. But we were ultimately limited by alignment errors that we discovered on during our benchtop tests. So what we effectively did is we created this other receiver that is identical in construction as our source, as our transmitter. So it's got a wire grid, it's got a tilt meter, and so the idea is that you should be able to understand the orientation of both of these instruments to very high precision, and that if you understand the entire system end to end, then you should be able to back out what the actual orientation is of the receiver and be able to compare that orientation to what you actually know it to be, right? But it actually turns out that there was a systematic effect that was impacting our ability to extract the correct angle, which was very sensitive to the pointing of our calibrator towards our receiver. And this is important because that means that this was also, because it was a physical effect, that this was also affecting our measurement on the telescope, which is ultimately what limited us to our zero point 0.3 degree systematic error because of our previous because I'm sorry, because of our priors on our RPS of our alignment of our instrument. That said, we do think that we understand things now. Our grad student Annie Polish has made a lot of effort this year to track down all of these miscellaneous systematics, and we have been able to actually back out the angle of the calibrator that we think we expect it to be, which is great. So that means that we have started a new calibration campaign at Pol. Uh, that is going to be ongoing throughout the next couple of months. So please stay tuned on that. If you're interested in understanding more about this effort, please go see Annie Polish's talk, as she will be explaining that in more detail. But in summary, we've made this very complex measurement with a bunch of different mechanical, observational, and analytical challenges. And we've considered many different sources of uncertainty, be it statistical or systematic. And while we are very proud of this measurement, and it's got it's a very rich data set, we were ultimately limited in our ability to constrain parity violation due to that remaining systematic uncertainty that I just mentioned, right? Um, but how do we go forward with applying this to the CMB? And while we can't look at real data, we can apply this calibration to simulations, and that's going to give us everything that we need to know as far as uncertainties and how things impact each other, except for that final answer. And so that's what we're going to do here is we're going to start looking at the CMB sims. Okay, first, before we talk about the Sims, we got to step back a little bit and talk about how the CMB is actually affected by cosmic birefringence, right? So when we're looking at the CMB, it usually comes in Stokes Q and U, but then we can do a basis change into what we call E and B, which is a curl-free and gradient-free modes. And on the left here, what you can see is if you have E modes and B modes, as if there is some sort of birefringence, then that linear polarization starts to get rotated, and over after a while there's you can't distinguish between what E and B actually looks like until if you're fully rotated, then E looks like B and B looks completely like E, right? And so we call this E to B or B to E leakage, right? And on the right here is in EE and BB and EB power spectrum. So in the case of birefringence, EE sort of looks the same. If you zoom in very close, you'll see that it starts to take on a different shape. But since there is no EB in theory, then the EB is starting to take on this very unique shape that is directly correspondent to the uniform rotation of E modes into B modes in the case that there are no B modes, right? And so if we take our CMB maps that are in T, Q, and U, we convert them into T, E, and B, we can convert those into angular power spectra, where on the right here you've got this thick black line is the mean of the power spectra under which we've been rotated, and the tiny gray lines are a realization of the universe that encompasses all sorts of different noise factors, including cosmic variance and instrumental noise, lensing, and so on and so forth. And then the way that we actually get angles is by taking that model of EE and rotating it into into EB, and then whatever angle minimizes those residuals is the angle that we get out from our fits. And for our fits, the way that we actually look at the angles, we look at them in three different ways where we have calibrated, uncalibrated, and then uncalibrated derotated. So calibrated is where the maps and the angular power spectra are made with angles from the calibration data. And then for uncalibrated, we have maps that are made with angles from the calibration data, and then but the angular power spectra doesn't actually have any idea of what the angles are, and we assume ideal from our pointing model. And then uncalibrated derotated maps are maps that are made with angles from the calibration data, and then the angular power spectra are actually derotated using a single angle that is coming from our calibration data. And this is actually useful because this is actually how we go about actually derotating the maps during self-calibration in our real data. And this is actually neat because this shows us biases that we would get from detector to detector polarization variation. Now, this is also useful for identifying the contributions into our uncertainty coming from the CMB, right? So we had the instrumental uncertainty coming from the telescope and the calibrator. Now we're looking at how the uncertainty contributions come directly from our CMB sims, right? So we've got just the good old CMB lambda CDM only, and then we have gravitational lensing. in galactic dust. And then there's also instrumental noise. And then we can also look at how they combine together in different ways. So for our error budget, what we did is we separated these into their constituent parts. So noise, we have the noise contribution, and we fit angles to the noise, and that gives us 0.06 degrees, which is our dominant, current dominant uncertainty. But this actually goes down as you include more data. So we're only using 2 years of BICEP3 data right now. So this is 2017 and 2018. We currently have up to 2023 that we can use. So the idea is that as we include more and more years, this is going to go down by a significant amount. And then we will be in this regime where we're actually limited not by noise, but by gravitational lensing in the B modes, right? And this could actually, this isn't a hard limit either. This would also go down by a delensing process, but that also requires using a large aperture telescope such as South Pole Telescope in order to do our to help with our delensing, right? So what we can also do is we can see, we can predict how this would go down using by using a very naive forecasting. We found that in our sims, the amount of residual BB signal in our power spectra directly contributes to variance on the angle. And so what we can do is we can draw linear dependence, and therefore if we reduce the BB signal by some amount, then that implies that we can get a reduction in the variance on our noise and our delensing. And that allows us to do some naive forecasting, right? So if we include up to 7 years going from 2, then we get down to 0.055. But if we include that for delensing, if we include delensing, that actually gets us down just a tiny bit more, right? So we're currently dominated by noise, but the best we can do is about 0.05, which is actually pretty significant, twice as good as what we've been able to, of what our goal has been. And so, in summary, we have used a ground-based polarized calibrator in order to determine the orientation of our instrument, which was the ultimate thing that was limiting our analysis. So the instrumental systematics were about 0.3 degrees, and our target goal was zero point 0.1. So that's what ultimately led us to not unblind. But in our CMB uncertainties, we're currently dominated by noise by zero point zero 0.06, which is immediately followed by lensing. That said, we are going to try again this year. We currently have all of our equipment down at the South Pole, and we are going to be making measurements in the next couple of weeks. So hopefully, we're going to have a completed analysis by this time next year. So please stay tuned on that. And lastly, we have a paper out on arXiv now. Please give it a read because this talk did not do it justice. And I look forward to talking with you all in a week.